In this lesson, we will study function operations and composition. We will perform arithmetic operations on functions, we will calculate the difference quotient, and we will look at the composition of functions and domain. So first of all, let's tackle operations on functions. So we have some definitions here that allow us to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x. Okay, so it's very intuitive here to find f plus g of x. We just add the respective functions, and same thing for the other operations. We do, however, need to be careful when we are dividing functions, and here we exclude values for g of x that would create a 0 in the denominator. In terms of the domain for f plus g, f minus g, and f times g, the domain will include all real numbers in the intersection of the domains of f and g. Right? And so the domain of f divided by g is likewise those in the intersection, but we have to exclude 0 from our domain. So let's look at some examples. So let's find f plus g of 1. So using the definitions that we just talked about, this simplifies into f plus 1, or f of 1, plus g of 1. And so here we're going to evaluate our function f at 1. So we're going to replace x in f with 1. So we get 1 squared plus 1, which is 1 plus 1, which is 2. Okay? So now we need to find g of 1. So we're going to go to our function g, and we're going to replace x in g with 1. So here we get 3 times 1 plus 5, so that's 8. Okay, now keep in mind the operation that is joining here, f of 1 and g of 1, is a plus. So we're going to need to bring that down, and then 2 and 8 will make 10. Okay, now let's find f minus g of negative 3. So using our definitions, we will write f of negative 3 minus g of negative 3. So like we did in the previous example, to evaluate f of negative 3, we are going to replace x in f with negative 3. So we have negative 3 quantity squared plus 1, and that'll be 9 plus 1, which is 10. All right, and then to find g of negative 3, we're going to simply replace x in g with negative 3. So that will give us 3 times negative 3 plus 5, which is negative 9, and 5, which is negative 4. Now let's keep in mind our operation here. We are subtracting, okay? So we're going to bring that on down. We're subtracting these values. Be careful with your signs, right? So here 2 negatives back to back will create a positive, giving us a final answer of 14. Okay, let's find, for this example, f plus g of x. So we use our definitions to split this up into f of x plus g of x. So we're simply going to add our functions together. So we get 8x minus 9 plus the square root of 2x minus 1. Now this is as simplified as our expression can get, so we're going to leave our answer just like that. And now we need to name the domain of this function. And so the domain would be the intersection of the domains of f and g. So the domain for f is all real numbers. The domain for g would be all values that would yield a value of 0 or greater underneath that radical. So we have 2x minus 1 is greater than or equal to 0. That means x is greater than or equal to 1/2. So our final domain is 1/2 comma infinity, including that 1/2 with a bracket. Okay, let's look at that same pair of functions, but now we're going to divide. So using our definition here, we divide f of x by g of x. So we have 8x minus 9 in the numerator and the square root of 2x minus 1 in the denominator. So we will leave our answer like this. to name the domain, we're going to look at the intersection of these functions, and we also, since we're taking a quotient, we have to make sure that this value, this g of x, is not equal to 0. Okay? We found in the previous example that the intersection of those domains is 1/2, comma, infinity, inclusive. But here, because we have to rule out a 0 in the denominator, we cannot include 1/2 in our domain. And so our domain is going to be 1/2, comma, infinity, with a parenthesis instead of a bracket. Okay, and so sometimes we perform operations on functions when we're given a graph. So let's do a couple of these problems. So we have here f plus g of 4. So we simply need to locate on our graph where f of 4 and g of 4 are. So f of 4 is right here. Okay, so that's the ordered pair 4, comma 9. G of 4 is right here. That's the ordered pair 4, comma 2. So if I want to find f plus g of 4, I just split that up as f plus 4 plus f of 4 plus g of 4. We already said that f of 4 is 9 and g of 4 is 2. 9 and 2 will make 11. Okay, now let's do one more of these here. Let's do f times g of 1. So here we'll use our definition, right? F times g of 1 to split it up into f of 1 times g of 1. So letting x be 1, we locate the points on our graph that we're interested in. So when x is 1, our function f is right here at 3, so 1, comma 3. When x is 1, our function g here has the order pair 1, comma 1. And so f of 1 is 3 times g of 1 is 1. So our final answer is 3. Okay, sometimes instead of graphs, we are given tables. So here, let's take a look at an example with a table. Okay, so we have our values for x, and we have our function f there. So in the second column, we have values for f of x, and then the last column are the values for g of x that correspond with the x's to the left. All right, and so we'll do a couple of these. Let's first of all do f minus g of negative 2. Okay, so f minus g of negative 2. We will use our definitions to split that up into f of negative 2 minus g of negative 2. Okay. Now f of negative 2 is just negative 3 minus, and now here's where the trouble comes in. G of x is undefined right here. Okay. And so therefore the entire expression here is undefined. So the answer to that would just be undefined. Okay, and so now let's look at f divided by g of 0. So that is just f of 0 divided by g of 0. So this time we are looking where x is 0, so that would be on this row. So we have f of 0 is 1, okay, and then g of 0 is 0. Now we notice that this expression is undefined because there's a 0 in the denominator. So the final answer for this is undefined, just like the first one was. Okay, and so here, let's evaluate using these functions. Let's find f plus g of 4 here. So f plus g of 4 equals f of 4 plus g of 4. So to find f of 4, I'm going to go to my function f, and I'm going to replace x with 4. So f of 4 is simply 2 times 4 plus 1, which is 9. Okay. And then g of 4, I'm going to replace x in g with 4. So I'll have the square root of 4, which is 2. 9 and 2 makes 11. Okay, now we're going to talk about the difference quotient. The difference quotient is something that you will need in calculus when we talk about derivatives and slopes of lines. And so we do want to be familiar with the difference quotient. Okay, now you'll notice the difference quotient is given by this expression, and there are essentially three parts, right? There's f of x plus h minus, and then we have f of x, and then we have h. So we need to plug in for each of those, okay? Well, h is what it is. There's nothing really to plug in there. F of x we're given, so we need to find f of x plus h. That means in my function f, I'm going to replace x with x plus h. So I have 2 times x plus h squared minus 3 times x plus h. Okay, and then I'm going to simplify. So expanding this binomial here, I have x squared plus 2hx plus h squared. All right, and then I'm going to distribute this negative 3. I get negative 3x minus h. Continuing to simplify, I'm going to distribute my 2. So I get 2x squared plus 4hx plus 2h squared minus 3x minus h. All right, and so now we have found f of x plus h, so we can simply substitute this expression in for f of x plus h, okay? So what we have then, when we're looking for f of x plus h minus f of x all over h, we end up with 2x squared plus 4hx plus 2h squared minus 3x minus h. Okay, that's my f of x plus h minus f of x. F of x is just 2x squared minus 3x all over h. And so we're going to simplify this. It's not quite as bad as it looks, because we see here that our quadratic terms, our quadratic x's subtract out, and also our 3x's, because this is going to make a positive, so these will cancel out. So what we're left with then is 4hx plus 2h squared minus h all over h. So simplifying that, then we have 4x plus 2h minus 1. Okay, and then looking back here, I see that I left off a 3, right, when I distributed. Let's go back and take a look at that and make sure that we fix that. So here when we distribute, there should have been a 3 on there, right? So minus 3h minus 3. There we go. Now we got the right answer. Okay, and so the last thing that we're going to talk about is composition of functions and its domain. So when we define a composition of functions, we use f of g of x with this little circle. The circle does not denote multiplication. It's read f of g of x. We can translate that composition notation into a much more familiar function notation, so that is equivalent to f of g of x. When we compose functions, we want to keep in mind that the domain of f of g is the set of all numbers x in the domain of f, such that g of x is in the domain of f. And we're going to take a look at an example, and so we'll find that it's not quite as complicated as it looks. Okay, so here we have f of x equals 2x minus 1, g of x equals 4 all over x minus 1. We want to find f of g of 2. So we're going to expand this by writing it in function notation. So we have f of g of 2, x is 2, And so here our inside function is g of 2. That means I'm going to replace x in g with 2. So I have f of, then g of 2, right, is going to be 4 all over 2 minus 1, which is f of 4 all over 1 is 4. To evaluate f of 4, I go to my function f and replace x with 4. So that'll give me 2 times 4 minus 1. So that's 8 minus 1, which is 7. Okay, and so here we have an example where we want to evaluate a function g of f of negative 3. So here we translate that composition notation into function notation. So this is the same as g of f of negative 3. So we look at the inside first and evaluate that. We need to find f of negative 3. That means we're going to go to our function f. We're going to replace x with negative 3. Okay, so that will give us 2 times negative 3 minus 1. Okay, so that's negative 6 minus 1, which is negative 7. Okay, and then finally plugging negative 7 in for g, we have 4 all over negative 7 minus 1, which is 4 all over negative 8, which is negative a half. Okay, we're almost done. All right, just a couple more problems here. We're going to find f of g of x and name its domain. So we translate this composition notation into function notation. Our inside function is g of x, so we're going to take g of x and put that inside of our function f. So in place of x in f, we're going to replace that with g. So we have 6 all over 1 all over x minus 3. And now we simplify. So in our denominator, we have, 1 minus 3x all over x. And that is because here, to get a common denominator, I just multiplied by x all over x. Okay. So now we have 6 all over 1 minus 3x all over x. We're going to multiply to eliminate that complex fraction, and our final answer is 6x all over 1 minus 3x. Okay, and now looking at the domain for that function, we notice here that the domain for f of g of x is going to be all real numbers, right? So we have to look at g of x. It can't be 0 because that would make g of x undefined. The domain of f is all real numbers except for 3. So the expression for g of x can't equal 3. So we determine the value that makes g of x 3, and we exclude it from the domain, okay? So we have to set 1 all over x equal to 3, again, because 3 would create a 0 in f. Then we have to make sure when we plug g of x inside of f that it's not 0, right? So 1 all over x cannot be equal to 3. So we will set it equal or not equal if you prefer to look at it that way, and we will solve. So here we have 1 can't be equal to 3x, and so x can't be equal to 1/3. So we are going to exclude 1/3 from our domain. So we exclude 0 because it would create a 0 for g, and we discard or leave out 1/3 because that would create a 0 for the composition function. So our final domain would be negative infinity comma 0 union 0 comma 1/3 union 1/3 comma infinity. So notice the values that we left out were 0 because that created a 0 in the denominator of g, and we left out 1/3 because that would create a 0 when we plug g into f. Okay, and the last problem that we're going to look at here is f of x equals 4x plus 1, g of x equals 2x squared plus 5x. And we want to demonstrate that g of f of x is not the same as f of g of x. So let's find each side, okay, separately, and then we'll show that they are not the same. So going left to right, let's find g of f of x. Again, translating that composition notation into function notation. We see that we're going to place our function f inside of g. So here, wherever we see an x in g, we're going to plug in this f of x in there, okay? So we have 2 times 4x plus 1 squared plus 5 times 4x plus 1, okay? We can simplify by expanding that binomial. So we'll have 16x squared plus 8x plus 1. We'll distribute our 5. So we have 20x plus 5. Now we'll continue simplifying. So we have 32x squared plus 16x plus 2 plus 20x plus 5. Okay, and so now we want to combine like terms. We have 32x squared. Combine our linear terms, so we have 36x. And combine our constant terms, which is 7. So g of f of x equals this quadratic. Now we want to find f of g of x. So let's do that, and then we're going to show that those are not the same. Okay, so f of g of x can be translated. Let's come underneath here, oops, as f of g of x. So inside of my function f, I'm going to replace x with g. So notice up here where I have an x in f, I'm going to replace that with g. So it's just a matter of plugging in. So here I have 4 times 2x squared plus 5x plus 1. Simplifying, I have 8x squared plus 20x plus 1. So f of g of x is this quadratic. Clearly, these two expressions